Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the second video on the CASCODE Amplifier design. In the first video, I covered the why and how behind this design. Now, if you missed that one, there's a link up in the corner for you and down in the description for your convenience. In this video, I'm going to dive into the circuit analysis and design of a CASCODE amplifier. I will be using bipolar junction transistors and the methodologies already covered in my previous videos on bipolar junction transistor circuit analysis. I will be specifically leveraging the methods for the beta-stabilized common emitter amplifier. I will also show both simulation and actual bench results for the design we arrive at here. Now, if you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, let's begin by defining the design requirements. In the last video, I revealed the basic circuit architecture of the CASCODE amplifier. That same architecture is what you see here. Now we get to actually design one of these things from the ground up. And we begin this process, like any other design process, by setting out our basic design goals. So let's talk about this just for a moment. First, our power supply, or VCC, is going to be 12 volts. Second, both transistors are going to be operating in their linear active region. After all, we want a linear amplifier. Third, the quiescent collector current of the upper transistor, Q1, will be defined as 1.5 milliamps. Number 4, the quiescent collector voltage of the upper transistor will be midway in the available voltage swing, giving us as much room on either side of that quiescent point as possible for the output to swing. I will assume a current gain, or HFE, of 100 for both transistors, and I will be using all of the standard rules of thumb that are used for a beta-stabilized amplifier for the common emitter portion. Okay, so let's begin this process by determining all of the currents that we can. Well, we know that Q1's collector current, or IC1, is 1.5 milliamps, and its current gain, HFE, is 100. We know that the quiescent base current is equal to the quiescent collector current divided by the transistor's current gain, or HFE. So, the quiescent base current is equal to 1.5 milliamps divided by 100. Which gives us a quiescent base current of 15 microamps. Now, what about Q1's emitter current? Well, it is equal to the sum of the collector and base currents. So the quiescent emitter current is equal to 1.5 milliamps, the collector current, plus 15 microamps, the base current, which gives us a quiescent emitter current of 1.515 milliamps. Now, the emitter current of Q1 is equal to the collector current of Q2, because, well, where else would the current go otherwise? This means that the quiescent collector current of Q2 is equal to 1.515 milliamps. And we know that the current gain, HFE, is equal to 100, so we can calculate the quiescent base current of Q2, IB2, the same way we calculated IB1. This means that the quiescent base current of Q2 is equal to 1.515 milliamps divided by 100, which gives us a quiescent base current for Q2 of 15.15 microamps. And then there is the emitter current for Q2, which is, well, as before, the collector current plus the base current, So the quiescent emitter current for Q2 is equal to 1.515 milliamps, that's the collector current, plus 15.15 microamps, that's the base current, and this gives us a quiescent emitter current for Q2 of 1.53015 milliamps. Okay, so the next steps. We will move to Q2's emitter. According to the standard rule of thumb for a beta-stabilized common emitter circuit with an emitter resistor, the voltage across the emitter resistor should be 1/10 of VCC, or 2 volts, whichever is less. In our case, VCC is 12 volts, so we have 12 volts divided by 10. This means that the voltage on the emitter of Q2 is equal to 1.2 volts. This, of course, is also the voltage present across the emitter resistor Re. So now we know the voltage across the emitter resistor and the current through it, so we can calculate the value of it using Ohm's law, which tells us that the value of the emitter resistor is equal to the voltage across it divided by the current through it. So we get that the value of the emitter resistor is equal to 1.2 volts divided by 1.53015 milliamps, which gives us an emitter resistor value of 784.2 ohms. Well, with this under our belts, we move to Q2's base circuit. Well, we know the voltage on Q2's emitter. That means that we can also calculate the voltage in the base of Q2. We can see here that the voltage in the base of Q2 is equal to the emitter voltage plus the base emitter voltage. And we know the voltage on Q2's emitter is 1.2 volts as calculated, and the base emitter voltage is 0.7 volts per our standard model. This gives us Q2's base voltage is equal to 1.2 volts, the emitter voltage, plus 0.7 volts, the base emitter voltage. So the Q2's base voltage is equal to 1.9 volts. Well, to begin with, you might be wondering why I'm going to be doing what I'm doing next with all of the Thevenin equivalent stuff. It is so that we can easily get at the needed values for the base biasing resistors. So, to that end, we're going to pull out yet another rule of thumb from the beta-stabilized common emitter circuit. Well, you remember the Thevenin equivalent circuit for the biasing resistors of the beta-stabilized common emitter circuit. It looks kind of like this. In that model, the base biasing resistors were labeled as R1 and R2, with R2 as the resistor between the base and ground. Our Thevenin is the parallel combination of these two biasing resistors. In our case, we say 3 resistors. The top 2 comprise R1 of the biasing resistor, so R1 is equal to Rb1 plus Rb2. R2 is the same as our Rb3. Now, we need to calculate the value of the R1 and R2 biasing resistors. And we begin this process with the rule of thumb for the value of R Thevenin, which tells us that the value of R Thevenin is equal to the value of the emitter resistor times the quantity, the current gain plus 1, all divided by 10. We know the emitter resistor, Re, is 784.2 ohms, and the current gain, or HFE, is 100. So the value of R Thevenin is equal to 784.2 ohms times the quantity 100 plus 1, all divided by 10, which gives us R Thevenin equal to 7.92042 k ohms. Well, now that we have the value of R Thevenin, we can calculate the voltage drop across it. We know from our work with the beta-stabilized common emitter circuit that the current through R Thevenin is the same as the base current Ib2. And, well, we know that Ib2 is 15.15 microamps from a previous calculation. With Ohm's law telling us that the voltage across our Thevenin is equal to the value of it times the current through it, we get that the voltage across our Thevenin is equal to 7.92042 k ohms times 15.15 microamps, which gives us a voltage across our Thevenin of 0.12 volts. Well, now we can turn our attention to finding Thevenin. To do this, we have to use Kirchhoff's voltage law. Now, following the loop around the base emitter of Q2, we know that Thevenin minus Thevenin minus the VBE, the base emitter voltage, minus VE2, the voltage on the emitter of Q2, is equal to 0. And we know that the voltage across our Thevenin, or Thevenin, is 0.12 volts, as we just calculated it. The base emitter voltage, VBE, is 0.7 volts from our standard model. And the emitter voltage, VE2, is equal to 1.2 volts from our rule of thumb. And this gives us Thevenin minus 0.12 volts minus 0.7 volts minus 1.2 volts is equal to 0. Rearranging stuff and solving for Thevenin, we get that Thevenin is equal to 2.02 volts. We are making real progress, and now that we know Thevenin, we can calculate the bias resistors R1 and R2. Utilizing the formulas presented in the video on the beta-stabilized common emitter amplifier, we know that R1 is equal to the quantity R Thevenin times VCC divided by Thevenin. Putting our known values into this, we get that R1 is equal to 7.92042 k ohms times 12 volts divided by 2.02 volts. And we get R1 is 47.052 k ohms. Now, for R2, which is the same as our RB3, this equation tells us that R2 is equal to the quantity of R1 times R Thevenin, all divided by the quantity R1 minus R Thevenin. Putting in our known values, we have that R2 is equal to 47.052 k ohms times 7.92042 k ohms, all divided by the quantity 47.052 k ohms minus 7.92042 k ohms, which gives us a value of R2, which is also the value of RB3, of 9.5236 k ohms. Now, let's step through the resistor chain that makes up our upper two bias resistors. To do this, we're going to have to determine all of the currents associated with this resistor chain. Well, we start this process with the current through RB3. Well, we already know the voltage across RB3 because it is the same as the base voltage of 1.9 volts. And we know the value of RB3, well, because we just calculated this as R2, and this is 9.5236 k ohms. Now, we put this into Ohm's law, which tells us that the current through RB3 is the voltage across it divided by the value of it. This gives us the current through RB3 is equal to 1.9 volts divided by 9.5236 k ohms. So, the current through RB3 is equal to 0.1995 milliamps. Now our next step is to determine the current through RB2, which is the current entering the node at the base of Q2. To do this, we write Kirchhoff's current law equation around the node at the base of Q2. We get IRB2, the current through RB2, plus IRB3, the current through RB3, plus IB2, the base current of Q2, where IRB2 is entering the node, so it is positive. IRB3 is exiting the node, so it is negative. And so we know that IRB3 is equal to minus 0.1995 milliamps. IB2 is also exiting the node, so it is negative. And we know that IB2 is now minus 0.01515 milliamps. Thus, our KCL equation becomes that the current through RB2, IRB2, minus 0.1995 milliamps minus 0.01515 milliamps equals 0. Rearranging this and solving for the current through RB2, we get that the current through RB2 is equal to 0.21465 milliamps. Now we can turn our attention to the current through RB1 by writing Kirchhoff's current law equation around the circuit node at the base of Q1. We have IRB1, the current through RB1, plus IRB2, the current through RB2, plus IB1, the base current in Q1, is equal to 0. Now, IRB1 is entering the node, so it is positive. IRB2 is exiting the node, so it is negative. And IRB2 is equal to minus 0.21465 milliamps from our last calculation. IB1 is also exiting the node, so it is negative. This means that IB1 is equal to minus 0.015 milliamps from an earlier calculation. Thus, the KCL equation becomes that the current through RB1 minus 0.21465 milliamps minus 0.015 milliamps is equal to 0. Rearranging this and solving for the current through RB1, current through RB1 is equal to 0.22965 milliamps. Now, we know all sorts of wonderful things, but we are now quite stuck unless we get some new information. And this is where we get to apply engineering knowledge and assume a feel-good number for our design. Well, we need to know either the voltage on the base of Q1 or the voltage across RB2. So how do we do this? We do this by applying our knowledge about these transistors which exist in their linear active region. We begin with the base collector junction of Q2. We know that it must be reverse biased. And so I'm going to assume that this must be at least 1 volt. Now we move up from the collector of Q2 through the emitter of Q1 to the base of Q1. The base emitter junction of Q1 must be forward biased for it to be in the linear active region. Now, our standard model assumes a voltage from the emitter to the base of 0.7 volts. All of this gets us from the base of Q2 to the base of Q1, which constitutes the voltage across RB2. So let's add this together to find the absolute minimum voltage we need to have. We get that the voltage across RB2 is going to be equal to 1 volt plus 0.7 volts. So the absolute minimum voltage across RB2 will be 1.7 volts. This is our absolute minimum voltage. But of course, we want a reasonable margin on this. So let's assume that this is going to be, 3 volts. Yes, I picked a number out of the air, but I picked it based on real information. So the quiescent voltage across RB2 is going to be 3 volts for our design. Now we can proceed to calculate the rest of the resistor values. So let's start with RB2. Ohm's law tells us that the value of RB2 is equal to the voltage across it divided by the current through it. And we know that the voltage across it, VRB2, is 3 volts from our, feel-good number. And we know that the current through it, IRB2, from a previous calculation, is 0.21465 milliamps. So we get the value of RB2 is equal to 3 volts divided by 0.21465 milliamps, which yields a value of 13.976 k ohms. Now, let's turn our attention to Rb1. We need to know what the voltage drop across Rb1 is so that we can calculate the value of Rb1. To find this, we will write the Kirchhoff's voltage equations around the base bias loop. And we get that the power supply voltage, VCC, minus Vrb1, the voltage across Rb1, minus Vrb2, the voltage across Rb2, minus Vrb3, the voltage across Rb3, is equal to 0. So what do we know? Well, we know that VCC is 12 volts by our design constraint. We have previously chosen to have Vrb2 equal to 3 volts, our feel-good number. We know that Vrb3 is the same as the base voltage of Q2, or 1.9 volts. So we get 12 volts minus Vrb1 minus 3 volts minus 1.9 volts is equal to 0. Solving for Vrb1, or the voltage across Rb1, we get a value of 7.1 volts. And so now we can apply Ohm's law that tells us the value of Rb1 is equal to the voltage across it divided by the current through it. And we know that the voltage across it is 7.1 volts, just as we just calculated, and that the current through it, Irb1, is 0.22965 milliamps from our previous calculation. So this gives us the value of Rb1 is equal to 7.1 volts divided by 0.22965 milliamps. So Rb1 is equal to 30.917 k ohms. But now we're faced with a bit of a conundrum. Well, we had previously said that R1 is equal to Rb1 plus Rb2. And we calculated a value of R1 of 47.052 k ohms. Now, we just finished calculating the values of Rb1 and Rb2. But when we add the calculated values together, we get that R1 should be 44.893 k ohms. But this is decidedly different than our 47.052 k ohms that had been calculated for R1. So what's up with that? Well, the value of R1 was determined assuming that this was a single resistor between VCC and the base of Q2. This means that the current through R1 was assumed to be equal to Irb2. Notice, however, that we have a disturbance in the midst of R1, the base current of Q1. So the current through Rb1 is greater than that of Rb2. As a result, we need a lower resistor value for Rb1 to maintain the required voltage drop across it with the higher current through it. The lower calculated value of Rb1 acts like a larger value than it actually is when viewed from the perspective of the voltage across it and the current through Rb2. This is why we had to calculate the value of Rb1 from its voltage drop and current flowing through it, and not by subtracting the value of Rb2 from our calculated value of R1. With this conundrum dissipated, we can now turn our attention to our last unknown component, the collector resistor Rc. Our design criterion says that the quiescent voltage on the collector of Q1 must be in the middle of the available voltage swing with Q1 and Q2 in their linear active region. So how do we determine what this available voltage swing is? It begins by determining the voltage on the base of Q1. And so how do we do this? Well, we work our way up from ground through the bias resistor string. So what do we know? We know that the voltage on the base of Q2, or VB2, is equal to 1.9 volts. This is the same as the voltage across Rb3. We previously set the voltage across Rb2 at 3 volts to ensure the proper operating condition for the base collector junction of Q2 and the base emitter junction of Q1. This brings us to the base of Q1. So the voltage on the base of Q1 is equal to the voltage on the base of Q2 plus the voltage across Rb2. Putting in our known values, this gives us that the voltage on the base of Q1 is equal to 1.9 volts plus 3 volts. So now we know the voltage on the base of Q1 is equal to 4.9 volts. Now, to be sure that the base collector junction of Q1 is reverse biased, the collector voltage must be no less than 1 volt above the base voltage. This means that the absolute positive minimum voltage we can allow on the collector of Q1 is 4.9 volts plus 1 volts, or 5.9 volts. The other hard stop is the power supply voltage, or VCC, which is 12 volts. Now that we know these limits, we can set the quiescent collector voltage for Q1 to be halfway between 5.9 volts and 12 volts. The difference between these two limits is equal to 12 volts minus 5.9 volts, which is 6.1 volts. Halfway between these two limits is 6.1 volts divided by 2, or 3.05 volts. Now, to get our desired quiescent point, I add this to the minimum collector voltage, so we get 5.9 volts plus 3.05 volts, which gives us 8.95 volts. Now, what is the voltage drop across the collector resistor? It is the difference between VCC and the quiescent collector voltage of Q1. This means that the voltage across the collector resistor is equal to 12 volts minus 8.95 volts, which tells us that the voltage across the collector resistor is equal to 3.05 volts. Our design criterion tells us that the quiescent collector current on Q1 is 1.5 milliamps. This is the same as the current through the collector resistor in this case. Now we turn once again to Ohm's law, which tells us that the value of the collector resistor is equal to the voltage across it divided by the current through it. This gives us the value for the collector resistor of 3.05 volts divided by 1.5 milliamps. And now we know the value of the collector resistor is equal to 2.03 k ohms. So the entire circuit now looks like this. Now, if we were going to realize this in a design for a product, our next step would be to sit down with a table of standard resistor values and choose the closest standard resistor values for the design. Then we would test this circuit to see if it meets our specifications. So now we ask, what is the anticipated gain of this circuit? Because the gain of the common emitter amplifier is essentially 1, we get at this answer by looking at the gain equation for the common base amplifier circuit. This is the gain equation for the common base amplifier, assuming that the source resistance is low. The gain is equal to the collector resistor value times the current gain of the transistor times the quiescent base current of the circuit, all divided by the thermal voltage of 0.026 volts. And we know that the collector resistor, RC, is 2.03 k ohms. We know that the current gain of the transistor, or HFE, is 100. The quiescent base current, or IBQ, is 15 microamps. And the thermal voltage, as I said before, is 0.026 volts, which gives us a voltage gain of 2.03 k ohms times 100 times 15 microamps, all divided by 0.026. Solving all this for voltage gain, we see that our voltage gain is equal to 117.11. So let's translate this to dB. We know that the voltage gain in dB is equal to 20 times the log to the base 10 of the voltage gain. Putting in the known value for the voltage gain of 117.11, we get that the voltage gain in dB is equal to 41.37 dB. Now, to fully experience the design in real hardware, I would have to create a PC board. The severe limitations placed on the design by implementing it with leaded resistors on a common breadboard would significantly warp the results. But I'm going to do this anyway, just because I'm curious. But first, I will demonstrate the performance of this circuit through the use of an LTSpice simulation using all of these ideal calculated values. Well, I have created the circuit in LTSpice and simulated it. You can see the results of this simulation here. Notice that the maximum gain is 40 dB and the calculated gain was 41 dB. Well, not too bad. You can see here that the upper end minus 3 dB point is at 5.281 megahertz. But, you ask, what is the advantage of this over the much simpler common emitter circuit? Well, to see this, I have to set up the simulation without the common base part of the circuit. But I have to be very careful here not to disturb the operating conditions of the common emitter circuit. The temptation would be to simply pop out Q1 and put a short between where Q1's collector and emitter were connected. But two things would change in the circuit if I do just this. First, the collector-emitter voltage of Q2 would change. Now, this would increase the amount of reverse bias in the base collector junction, reducing the base collector capacitance. So, we have to make sure that we maintain the same collector-emitter voltage on Q2. To accomplish this, I will use a separate power supply for the collector voltage supply. Second, the bias current on Q2 would change. Now remember, Q1 was drawing base current from this bias resistor string, which, well, it would no longer be drawing that. We have to add a current source to that point where the base was connected so that the bias current for Q2 would also remain the same. So, now the circuit looks like this in LTSpice. Here is the separate power supply for the collector. And here is the current source to simulate the existence of Q1's base. So what are the simulation results? Well, here are the frequency response results of both versions laid side by side. Notice that the minus 3 dB drop-off for the plain common emitter amplifier sits at 579 kilohertz. The CASCODE amplifier's high-end response is at 5.281 megahertz, and well, that's almost 9 times greater than the plain common emitter circuit. Okay, so what about the breadboard results? Well, my first step was to select standard resistor values for each of the resistors in the design. Then see if I could somehow find these in my collection of resistors. Well, here are the pictures of my very ugly breadboard setups. The one on the left is the whole CASCODE amplifier. On the right, you can see the modified CASCODE amplifier missing its Q1 and the addition of a resistor to draw Q1's base current, as well as the separate power supply connection for the collector power. You can see that I had to use multiple resistors to achieve the right values. Now, there's added inductance with the long leads of all these different resistors. Additionally, the breadboard itself has a lot of capacitance associated with its side-by-side rows of connections. And with all of this in mind, I didn't have very high expectations for its performance. So, let's see what the actual measurements came out to be. Here are the measurement results placed side by side on the same graph. The high-end frequency response of the common emitter amplifier rolls off at about 363 kilohertz. But the high-end frequency response of the CASCODE amplifier rolls off at 2.083 megahertz. This is almost 6 times greater than the plain common emitter amplifier. That is still not too bad considering, well, the mess that the breadboard experiment is. I'm sure that if I had created a dedicated PC board using all surface mount components, that the frequency response of the completed assembly would rival that of the simulation. Well, it is an amazing thing, this CASCODE amplifier. By just adding a single additional transistor to the circuit, we can push the high-end frequency response out a whole lot. And now you know how to design one and why they work like they do. Now, if you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.